To determine the load on a panel board, let's analyze the provided example. The panel board is fed by a 208Y/120 volts transformer and has three loads. Firstly, there's a 208 volts, three-phase 2000 watts load fed from a 3-pole breaker. Secondly, a 208 volts, single-phase, 1000 watts load fed from a 2-pole breaker on phases A and B. Thirdly, a 120 volts, single-phase, 500 watts load fed from a 1-pole breaker on phase C. We will assume unity power factor. For the first load, which is 2000 watts, three-phase, we can use the formula power equals 1.732 times voltage times current. Since the power is 2000 watts and the voltage is 208 volts, we can rearrange the formula to solve for current. Current equals power divided by 1.732 times voltage. Plugging in the values, current equals 2000 watts divided by 1.732 times 208 volts, which gives us a line current of 5.55 amps on phases A, B, and C. Next, let's calculate the current for the second load, which is 1000 watts, single phase at 208 volts. We use the formula power equals voltage times current. So, current equals power divided by voltage. In this case, current equals 1000 watts divided by 208 volts, which equals 4.81 amps on phases A and B. Finally, for the third load, which is 500 watts, single phase at 120 volts, we again use the formula current equals power divided by voltage. So, current equals 500 watts divided by 120 volts, which equals 4.17 amps on phase C. Now, let's combine the loads on each phase. On phase A, we have 5.55 amps from the three-phase load and 4.81 amps from the single-phase 208 volts load, totaling 10.36 amps. On phase B, we have 5.55 amps from the three-phase load and 4.81 amps from the single-phase 208 volts load, totaling 10.36 amps. On phase C, we have 5.55 amps from the three-phase load and 4.17 amps from the single-phase 120 volts load, totaling 9.72 amps. Therefore, the loads are as follows. Phase A has 10.36 amps, phase B has 10.36 amps, and phase C has 9.72 amps. To answer the question of what the load on the panel is, we identify the highest current draw among the three phases. In this case, phases A and B have the highest current draw at 10.36 amps. Therefore, the load on the panel is 10.36 amps, considering the leg with the highest current draw. In summary, the load on this panel is phase A 10.36 amps, phase B 10.36 amps, and phase C 9.72 amps, totaling 30.44 amps. To further elaborate on these calculations, let's break down each component and the formulas used. Firstly, understanding the power formula is crucial. Power, measured in watts, is the rate at which electrical energy is transferred. The basic formula is power equals voltage times current, or P equals V times I. This formula applies directly to DC circuits and single-phase AC circuits with a unity power factor, which we assumed in this example. For three-phase circuits, the formula is slightly different to account for the three phases. The formula becomes power equals 1.732 or the square root of 3 times voltage times current. This factor of 1.732 arises from the phase difference between the three phases in a balanced three-phase system. Now, let's revisit the calculations for each load individually. For the 208 volts, three-phase, 2000 watts load, we use the formula power equals 1.732 times voltage times current. Rearranging to solve for current, we get current equals power divided by 1.732 times voltage. Plugging in the values, current equals 2000 watts divided by 1.732 times 208 volts. This results in a line current of approximately 5.55 amps per phase. It is important to note that in a balanced three-phase system, the current in each phase should be equal. This ensures that the load is evenly distributed across the three phases, which is desirable for efficient operation. Moving on to the 208 volts single phase 1000 watts load, we use the formula power equals voltage times current. Solving for current, we get current equals power divided by voltage. Plugging in the values, current equals 1000 watts divided by 208 volts, which equals approximately 4.81 amps. Since this is a single-phase load connected between two phases, phases A and B in this case, the current flows through both of these phases. Therefore, we added this current to the existing current on phases A and B from the three-phase load. Lastly, for the 120 volts single-phase 500 watts load, we again use the formula power equals voltage times current. Solving for current, we get current equals power divided by voltage. Plugging in the values, current equals 500 watts divided by 120 volts, which equals approximately 4.17 amps. This single-phase load is connected between one phase, phase C in this case, and neutral. Therefore, the current only flows through phase C, and we added this current to the existing current on phase C from the three-phase load. When combining the loads on each phase, we simply added the individual currents from each load that contributed to that phase. This gives us the total current on each phase. Phase A has the current from the three-phase load in the 208-volt single-phase load. Phase B has the current from the three-phase load in the 208-volt single-phase load. Phase C has the current from the three-phase load and the 120-volt single-phase load. The phase with the highest current draw determines the overall load on the panel board. In this case, phases A and B both have the highest current draw, which is approximately 10.36 amps. Therefore, the load on the panel board is 10.36 amps. It is important to note that this calculation assumes a unity power factor, which means that the voltage and current are perfectly in phase. In reality, many loads have a power factor less than 1, which means that the voltage and current are not perfectly in phase. This can affect the accuracy of the load calculation. To account for a non-unity power factor, you would need to know the power factor of each load and adjust the calculations accordingly. The formula for power in this case becomes power equals voltage times current times power factor. This would result in a higher current draw for the same amount of power if the power factor is less than 1. Furthermore, it is important to consider other factors when determining the load on a panel board, such as the diversity factor and the demand factor. The diversity factor is the ratio of the sum of the individual maximum demands of the various loads to the maximum demand of the entire system. The demand factor is the ratio of the maximum demand of a system to the total connected load of the system. These factors can be used to reduce the calculated load on the panel board, as it is unlikely that all of the loads will be operating at their maximum demand simultaneously. In conclusion, calculating the load on a panel board involves summing the individual currents from each load on each phase, taking into account the voltage, power, and power factor of each load. The phase with the highest current draw determines the overall load on the panel board. It is also important to consider other factors such as the diversity factor and the demand factor to accurately determine the load on the panel board. These calculations are essential for selecting the appropriate size of the panel board and the associated circuit breakers to ensure safe and reliable operation of the electrical system. To reiterate the key concepts, firstly, understanding the fundamental power formulas for both single-phase and three-phase systems is critical. Power equals voltage times current for single-phase, and power equals 1.732 times voltage times current for three-phase. Secondly, accurately determining the current draw for each individual load is essential. This involves using the appropriate power formula and rearranging it to solve for current. Thirdly, correctly assigning each load to the appropriate phases, whether it is a single-phase load connected between two phases or a single-phase load connected between one phase and neutral, is important. Fourthly, summing the currents on each phase to obtain the total current draw on each phase is required. Lastly, identifying the phase with the highest current draw is necessary to determine the overall load on the panel board. In addition to these calculations, understanding the concepts of power factor, diversity factor, and demand factor can provide a more accurate assessment of the actual load on the panel board. These factors can help to avoid oversizing the panel board and the associated circuit breakers, which can save costs and improve the efficiency of the electrical system. Remember that accurate load calculations are crucial for ensuring the safe and reliable operation of electrical systems. The overloading a panel board can lead to overheating, insulation damage, and potentially fires. Therefore, it is essential to perform these calculations carefully and to consult with a qualified electrician if you have any doubts or concerns. To provide a more comprehensive understanding, let's delve into the practical implications of these calculations. Firstly, the calculated load on the panel board directly influences the selection of the appropriate size of the main circuit breaker feeding the panel board. The main circuit breaker must be rated to handle the maximum current draw of the panel board without tripping. Secondly, the load calculations also determine the size of the individual circuit breakers for each branch circuit connected to the panel board. Each branch circuit breaker must be rated to handle the maximum current draw of the load connected to the circuit. Thirdly, the load calculations impact the selection of the appropriate wire gauge for the conductors feeding the panel board in each branch circuit. The wire gauge must be large enough to carry the maximum current draw without overheating. The National Electrical Code (NEC) provides guidelines for selecting the appropriate wire gauge based on the current carrying capacity of the wire. For instance, NEC Table 310.15, formerly 310.16, specifies the allowable ampacities of insulated conductors rated up to 2000 volts, based on the insulation type and the ambient temperature. Fourthly, the load calculations are essential for ensuring that the voltage drop in the electrical system is within acceptable limits. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the system. The NEC recommends that the voltage drop in a branch circuit should not exceed 3% and the voltage drop in the feeder should not exceed 5%. To minimize voltage drop, it is important to use the appropriate wire gauge and to keep the length of the conductors as short as possible. Fifthly, the load calculations are crucial for determining the appropriate size of the grounding and bonding conductors in the electrical system. Grounding and bonding conductors provide a path for fault current to flow back to the source, which helps to protect against electrical shock hazards. The size of the grounding and bonding conductors must be adequate to carry the maximum fault current that could occur in the system. The NEC specifies the minimum size of grounding and bonding conductors based on the size of the ungrounded conductors. Finally, the load calculations are necessary for complying with local electrical codes and regulations. Electrical codes are designed to ensure the safe and reliable installation and operation of electrical systems. Compliance with these codes is essential for protecting people and property from electrical hazards.